Hello and welcome to podcast.init, the podcast about Python and the people who make it great. You can subscribe to our show on iTunes, Stitcher, or TuneIn Radio, or add our RSS feed to your podcatcher of choice. You can also follow us on Twitter or Google+, and please give us feedback. Leave us a review on iTunes, send us a tweet, send us an email, or leave us a message on Google+. You can also leave a comment on the show notes on our episode on our site at pythonpodcast.com. I would like to thank everyone who has donated to the show. Your contributions help us make the show sustainable. For details on how to support the show, you can visit our site at pythonpodcast.com. I would also like to thank Hired, a job marketplace for developers, for sponsoring this episode of podcast.init. Use the link hired.com/podcastinit to double your signing bonus. Linode is also sponsoring us this week. Check them out at linode.com/podcastinit and get a $10 credit to try out their fast and reliable Linux virtual servers for your next project. We are recording today on November 2nd, 2015, and your hosts as usual are Tobias, Macey, and Patti, though Chris might join late today. Today we're interviewing Erik Tollerud about AstroPy. Erik, could you please introduce yourself?
Hi, yes, I'm Erik Tollerud. I'm one of the coordinators of the AstroPy project.
And how did you get introduced to Python?
Well, I guess I started Python as an undergraduate student, actually, when I was doing an electronics course. Where I happened upon a software-defined radio project called the USRP, and it was after I spent a little bit of time just sort of fiddling around with it, I realized what you're really supposed to do is use this weird language called Python to program the radio, and that forced me to learn at least just enough Python to get along. And ever since then, I've used it for essentially all my work.
And what was the inspiration to create AstroPy, and what kinds of astronomical research can it be used for?
Well, the inspiration to create AstroPy sort of came from the fact that 4 years ago, I guess now, 4 or 5 years ago, there had been a lot of discussion about the problem that there were a lot of little libraries to do a lot of standard things in astronomy. And all of these libraries were overlapping somewhat in functionality, mostly incompatible, each programmed by sort of one person who was writing it as they had the time. And this was clearly a huge waste of resources. So we essentially got together and said, well, maybe we should just work together on a project. And since then, it has sort of morphed into a much larger beast that is even supported by some actual funded astronomical institutions, universities, and so on. To do pretty much the basics of most kinds of astronomy research that's available today. So it's sort of a underlying library, you might say. It's not aimed at at least the core part of it is not aimed at one specific type of AstroPy research. It's meant to be able to be the underpinnings of just about any kind of research.
So that's interesting that the impetus for its creation wasn't just because somebody saw a need in the space and created a library. It was actually because too many people saw a need in the space and were creating disparate libraries. And so it sounds like AstroPy was created as a way to unify all of those and provide a common interchange format between them so that people could more easily plug in the bits that they actually needed without having to rewrite everything from scratch every time.
Yeah, exactly. And also as a sort of a learning opportunity, because it was right around the time. So up until the last year or two, really, a lot of astronomy research is done using this programming language called IDL, which is sort of comparable to MATLAB, but is somewhat different in very subtle ways, but that is known almost entirely only by astronomers in certain key parts of the defense industry. And that was what a lot of astronomers did all of their day-to-day research in. But there were a variety of reasons why more and more people started realizing, well, this is not the best choice. So they've been switching a lot to Python recently. And that's what sort of led to this getting critical mass, was that previously was sort of a hobby thing where a few random astronomers used it. But there has been a shift recently from this IDL language to most at least new scientists working in Python.
Yeah, so it definitely sounds like Python would provide a pretty big boost, both in terms of being more accessible to more people because of the syntax of Python itself, but also being accessible to people outside of the realm of astronomy, so maybe people from other sciences or even just the average layperson who doesn't have the time or inclination to learn IDL specifically for doing astronomical research.
Yeah, absolutely. And the other thing is that, Python is, of course, free and open source. IDL is not. IDL, you have to pay a large licensing fee for each installation. So by having it be Python, a lot more, less well-funded universities and colleges could actually take part in astronomical research.
Yeah, I was curious about that because when you likened it to MATLAB, I know that one of the complaints I've heard a number of times about MATLAB is the licensing costs. And so I was curious whether IDL had the same stigma, which it sounds like it does.
Yep, absolutely.
So first off, guys, I apologize for joining late. My company's hair was on fire and I had to put it out.
No problem.
So my question is, can you tell us what AstroPy's modeling functions are and give us an example of where they might be used?
So the functionality in AstroPy surrounding modeling, so this is the AstroPy.modeling subpackage. I guess I haven't said that yet. AstroPy is built around a variety of subpackages that all live inside the AstroPy namespace that sort of cover various different functionality that astronomers often want. So the modeling subpackage is based around basically generically fitting models to data. So a more concrete example might be a spectrum. So you take the light from, say, a star, you pass it through a prism or a grating or something like that. You spread its light out on a CCD, and then you can see there are bright areas which correspond to, say, emission lines. And this is interesting for a variety of reasons in astronomy that maybe we don't have time to dwell on right now. But the key is you often want to fit particular quantitative models to that spectral line. So you need to take a one-dimensional representation of how much light there is as a function of wavelength, and then you want to fit some model to it, say a Gaussian or a Lorentzian. And the AstroPy modeling subpackage is meant to do exactly that and make that sort of 2 or 3 lines of code.
And so when you refer to it as a subpackage, does that mean that you can actually install the different subpackages independently of each other so that you can only install the bits that are actually being used, or does it all get pulled in at once when you install AstroPy?
Well, so modeling is a subpackage that is the second one. So it all gets pulled in at once when you install AstroPy. We have a different class of projects which are sort of loosely coupled, you might say, to the AstroPy core library, which are called affiliated packages. So they are separately installable. You can pip install those. They all depend on AstroPy and are sort of part of a wider community of people who agree to sort of work together and share interfaces, but they aren't part of the AstroPy core library, whereas modeling is. Modeling is a subpackage that you actually imported as AstroPy.modeling.
And this leads into a question I have about, I know that in academia and a number of the hard sciences, there isn't as much of a focus of rigor put on the act of software engineering and managing libraries and dependencies and versioning, etc. So I'm curious if there are any considerations that you need to be aware of and that you had to account for when writing libraries like AstroPy for practitioners of the hard sciences that would be different if the target audience were software engineers.
Oh, absolutely. This is probably the hardest thing of the whole project, is trying to sort of convince astronomers who are generally not terribly well versed in software. Many of them have had no formal education in software, even though probably 80 to 90% of everyone's job is either writing papers or writing code that goes into the papers they're about to write. Data analysis code. Yet easily half of them have no formal training at all in software and just had to sort of pick it up as they go along. This is common in a lot of the hard sciences, but it's particularly acute in astronomy because we're very software oriented. We generally a relatively small fraction of us work with actual lab apparatus. Most of us take data from a telescope and then spend months analyzing that, and that's all in the software. Yet many of us don't have formal software training. I do actually, but many astronomers do not. So we have to figure out how to write tools that are modern tools using modern techniques while still sort of hiding the more complex side of that. Like, for example, object-oriented programming. Many astronomers don't really know what that means, so we have to sort of sneak it in there, right? Which Python is very good at. Python, everything is an object, and you can just interact with things in sort of intuitive ways. But we often have to write code hiding the fact that it's object-oriented and instead just tell them there's this thing you can call, and it's sort of like a function, but not exactly.
And so it sounds like the majority use case for AstroPy and its associated modules is going to be in more of an imperative script style approach as opposed to doing, like you said, OO or functional programming.
It's a mix. So it's some like that. Recently, there's been a shift, I would say, because of the advent of the IPython notebook, which you may or may not be familiar with.
Yes.
You are familiar. Okay. So the IPython notebook has made it so that, it's sort of looks like a script, but it really is done sort of in between a script and an interactive workflow. And this appeals to a lot of the way a lot of astronomers operate. And I think there's been a gradual shift more in that direction just in the last, again, couple of years. But it is true that for most astronomers, it's going to be more like a script or, sort of very loose sort of functional programming rather than anything more advanced or more complex than that. There are a few exceptions. Like I use object-oriented programming all the time, but that's, like I say, because I have the background to do it. And many astronomers just either don't have the experience or don't have the time to learn how to do that.
Yeah, there's a project that I'm aware of who we're actually going to be interviewing next week called Software Carpentry that I know focuses on teaching academics and people in the hard sciences some of the best practices around software engineering, such as version control and some of the ideas around software design patterns. So it's definitely interesting talking to somebody who both works in the hard sciences and also maintains a library meant for that target audience, and hearing some of the challenges that go along with maintaining a library to make it usable and accessible to people who don't have that hardcore software background.
Yeah, absolutely. And that's, like I say, that's one of the hardest things, is how to make it both, easier to maintain by using these more advanced organizational techniques and useful to people who know them, while still at the same time sort of softly falling back on more simple methods when it makes sense. It's a very difficult edge to walk along, but it's what we try to do.
And you also mentioned IPython Notebook, and I'm curious if there are any libraries or additional modules that provide any tighter integration between AstroPy and the notebook itself.
So we've more tried to take the effort to go the other direction. So there are a lot of objects in AstroPy that interact well with notebooks. So if you just type the name of the object and execute the cell, for example, we have a table class that will sort of prettily format itself, and it uses some of the hooks that IPython notebooks have written to make that possible. So we don't have like an interface library or anything like that. We just have things that work well in the notebook and then gracefully degrade into a slightly less pretty appearance when you run them not in a notebook context.
And I imagine that the ability to render inline images in the notebook would become pretty handy in astronomy, because I'm assuming that there would be some visualization of that data and perhaps even imagery associated, being pulled from the telescopes.
Yep, absolutely. Yeah, that's one of the places. In fact, this has been something I've been working on just this last week, is trying to develop more. So there are sort of fully functioning astronomical image viewers that are aimed at particular astronomy formats. And it's a little difficult right now to get those to interface well with the notebook. But a project that I've been working on just recently is to do exactly that. Use some of these hooks to connect the very astronomy-specific tools that already exist to the wider notebook environment.
You mentioned Gaussian analysis earlier. I've heard of Gaussian analysis in the context of image processing in terms of sharpening images. Is that what you folks use Gaussian analysis for in astronomy?
So Gaussians appear in many different places in astronomy just because they have convenient statistical properties. What I was talking about before was taking not a two-dimensional Gaussian, which is used sometimes in astronomy, but rather a one-dimensional Gaussian, because a spectrum, usually you take an image of a spectrum that's projected onto a 2D imager, but then you collapse it essentially down into a one-dimensional thing that just says how much light came in as a function of color or wavelength. And you fit a Gaussian to that one-dimensional thing, not a two-dimensional Gaussian.
Gotcha. So what are some of the most interesting applications that AstroPy has been used for?
Let's see. So AstroPy is a nuts and bolts library in a lot of ways. So, for example, some of the beautiful images you see on Hubble site of images taken by the Hubble Space Telescope have certainly been processed with either directly or someone who took those observations, planned those observations using AstroPy. But it's hard to. So AstroPy is very much a nuts and bolts library, so it's a little hard to say what a specific application is that AstroPy has been used for. It's sort of right. Most people who work in Python and do astronomy have used AstroPy a little bit here and there for some part of the process.
I'm sure it's also true that as a library writer, people who are using your library for cool things don't necessarily report back, so it's probably hard for you to even be able to say, right?
Absolutely, it's a huge challenge. In academia, we have this extra problem that a lot of your career advancement in academia is driven by writing papers. And, especially in astronomy, which is not, even though we use software all the time, software is not necessarily thought of as being an integral piece of doing astronomy. You need people to cite it whenever they use AstroPy, and we're probably massively undercited given how many people we know are using it relative to how many citations we've gotten. And that's the thing that gets you career advancement in academia in a lot of ways.
And so are there open data sets that are available for people outside of academia to do analysis of astronomical data using AstroPy?
Yes, absolutely. So there are some open data sets that are actually integrated into our tutorials website. So it's just tutorials.astropy.org. And there's a couple of those tutorials that just have data sets that we've put up there, basically, that someone has observed, say, the spectrum of a star. Actually, that's one of them, as I was mentioning earlier. Someone has observed the spectrum of a star, and they uploaded it onto one of our data server we're using. And when you run through the tutorial, you actually download that data set, and you process that data set using AstroPy tools. And there are many other kinds of open data that are available in astronomy, that some of which can be accessed directly from AstroPy, primarily through the AstroQuery affiliated package. There's something like 20 different tools that are part of AstroQuery that access 20 different places where you can download data. By and large, it's mostly open. This is sort of the culture in astronomy, that most data that gets taken after a certain period of time, usually 18 months, maybe 2 years, becomes open so that anyone can use it at any time.
And are you aware of any useful or breakthrough discoveries that have been made by people outside of academia using AstroPy to analyze that information?
So that goes back to the same problem before of almost certainly yes, but it's a little hard to tell. They used AstroPy as part of the project. As part of making an significant discovery that they wrote up in a journal paper, they said they used AstroPy, but it's hard to say whether they used AstroPy to download the data or they used AstroPy to reprocess the data into a form that was easier for them. So it's a little hard to say, to give a very specific example of that. But there have certainly been significant discoveries more recently.
Could you please tell us about AstroPy's virtual observatory capabilities?
Sure. So the virtual observatory is a very specific thing. So virtual observatory is a standard that was developed by an international consortium of organizations that do astronomy, basically. And AstroPy provides, and they set a bunch of standards essentially to how to access astronomy-specific data sets, right? Like a specific standard way to download spectra of stars, for example, since that was the example I was giving before. AstroPy essentially provides an interface layer that lets you use those standards. And that's mostly what it is. Now, to be honest, that functionality has not been used a huge amount because the standard has not been as widely adopted as I think the original thought was it was going to be. But it is there for data sources that use the VO, as it's called.
Gotcha. What are some interesting use cases for AstroPy's cosmological calculations?
So AstroPy.cosmology is another one of the subpackages in AstroPy. And it's essentially intended to be a way to do many of the standard cosmological calculations that are done by sort of regular, anyone who's either doing actual astronomical research or who's, say, an undergrad who just wants to understand the relationship between redshift and look-back time. So the universe is expanding, so that's just a fact that we know about the universe. And there's a specific relationship between how quickly it's expanding and how far away something is. So that's the redshift distance relation. And AstroPy.cosmology gives you a way to just, and the calculations involved in figuring out exactly how to do that connection can be very complicated. There are pages of complex integrals in textbooks that you learn in sort of a graduate level cosmology course. But AstroPy.cosmology has sort of locked these away in functions that just have relatively straightforward names like redshift to look-back time. So you can ask, for example, how old the universe is by simply asking what was the look-back time to a redshift of infinity. And anyone could just download AstroPy and do this and get a rough sense of how the universe is expanding.
And are there other libraries available that provide similar capabilities, perhaps in other languages? And what makes AstroPy unique among them?
So there are a lot of different versions of the various pieces that go into AstroPy. I don't know that there's a library that has all of these pieces put together in one place. There is a very standard library called Astron in IDL, that rather obscure language that is known mostly to astronomers and parts of the defense industry, that has a lot of the same functionality, although often expressed in very different ways. IDL, for example, only very recently supported object-oriented programming, so as you might imagine, the interfaces look totally different from Python, where it's baked in from the beginning. But there are a number of libraries in a variety of different languages that have been used in the past by astronomers that do a lot of this stuff. And moreover, even in Python, there are a lot of overlapping libraries that do some of the functionality that's in AstroPy. What AstroPy has that I think makes it unique is that it's in Python, which is a very efficient language to do sort of quick data work, which is what most of what astronomers are doing is quick data analysis. And it provides sort of a one-stop shop, right? Instead of having to pull together 6 different libraries to do basic tasks that you learned you need to know how to do as a graduate student, let's say, in astronomy, or even an undergraduate. But you don't want to have to code up all of those little pieces yourself. AstroPy provides you one place to do it with one consistent interface and high-quality documentation so that you don't have to spend a lot of time messing around trying to figure out just how it works before you can even get your research done.
So can AstroPy consume data directly from telescopes and other observational apparatus?
Yes. So it depends on, since AstroPy is a library, sort of a plumbing level library, AstroPy, the core library, AstroPy, doesn't necessarily take in data and provide you with, for example, analyzed, reduced, as we call it in astronomy, reduced data just straight out of the box. But it does provide a lot of tools that let you take data in some weird, obscure format that the telescope output and put it in a more generally useful format that then you can feed into other tools. In fact, I'm going to a telescope tomorrow, and I plan to use AstroPy for exactly that purpose.
And I'm sure the amount of data generated from observing astronomical phenomena must be pretty immense, and I'm wondering what are some of the tools that are used to manage that data, and how does AstroPy interface with them?
Yeah, so there's definitely a lot of different levels of either big data, as you might call it, or just large amounts of data in the sense of you take an image once every few minutes. Each image is, a few gigapixels in size or something like that, and you have to figure out how to keep up with this. AstroPy is designed around some of these sorts of workflows to make this at least conceivable. And one of the main tools we use is Cython. So Cython lets you essentially write C code in Python-like syntax. So it lets you write code that you can compile down to something very quickly, or something that runs very quickly, while still writing it in a Python-like syntax. And it provides a lot of very smooth ways of interfacing between the Python level and the Cython level. So we often use this for pieces of the code that we know are going to be very computationally intensive when you feed the output of observations into it. So we try to write as much as possible in Python, then we profile the code, we say, oh, this is a spot that is running really slow because there's a for loop, and this for loop has to go over every single pixel in the imaging data. So let's put that in the C-level code where the for loops will run much more quickly, and let's do that with Cython.
How might AstroPy be used to prove or disprove the cold dark matter hypothesis?
So AstroPy, again, on its own is not particularly useful as a tool for proving particular hypotheses, but it gives us a toolbox you can use to work towards understanding what's going on with your astronomical topic of interest. So in the specific case of cold dark matter, for example, you might need to take observations of stars in a satellite galaxy near us, so a small galaxy that orbits around the Milky Way. It turns out if you take spectra of those stars, you see that they're moving much more quickly than they would be if there were if the only matter there was the stars themselves. So the fact that they're moving that much more quickly means there's a lot of mass, and that mass is dark matter. And in fact, it turns out that cold dark matter, as opposed to some other hypotheses like warm dark matter, behaves much, much different on the scales of these tiny galaxies. So you can analyze data sets, and in fact, this is a lot of what I do, is analyze data sets of spectra of small galaxies, or of stars in small galaxies. And by analyzing these and determining how fast the stars are going, something I do with AstroPy, you can ask whether or not these galaxies are consistent with cold dark matter or some other form of dark matter, or no dark matter at all.
And what are some of the architectural choices that have been made to allow for the AstroPy library to serve as the core for such a large number of other add-ons? And does AstroPy provide a common data format to allow for easy interoperability between those add-ons?
So we'll start with some of the architectural choices. So AstroPy has been, it was not originally written in this way, because when it started, we were just trying to build a unified library around some of these core ideas. But it turned out that a lot of the stuff we had to do in this process, like writing good documentation efficiently and quickly, and tools for making Cython work very smoothly with Python, which I mentioned earlier, turned out to be things where people would then come to us and be like, oh, that's cool. I want to write this affiliate package that does this particular, very niche domain-specific task in astronomy, but I want to be able to use all of those other things that I see you're using. So what we ended up having to do is sort of take those pieces and separate them out into a different package, which we call AstroPy helpers, that can be installed separately from AstroPy and can be used either alongside AstroPy or just by itself as a way to make it easier for these other packages to write code that looks very similar to AstroPy code, so that when someone else comes along and wants to contribute or work on the code, they recognize it as being similar to the kind of code they've seen before. So that's sort of the main architectural choice that's made a difference, is that we try to share both code style and sort of code support tools like testing, documentation, and compilation when quality or when fast code is needed. Right, so those are the key architectural pieces. Another level that fortunately can be somewhat separated from that is common data formats. So this is one of the main things that AstroPy is trying to do. So for example, we have a class that is meant to represent celestial coordinates. You want to know where that star is in that spot in the sky and that galaxy is in that other spot in the sky. And I don't want to have 6 different ways of representing that point in the sky. So AstroPy provides a SkyCoord class that does exactly that. And the idea is all of these affiliated packages, when they need a sky coordinate, a position in the sky, they use the SkyCoord class and they don't have to write it themselves. They can just use the AstroPy version. Similarly, we have representations of 2-dimensional data sets like the kind you get when you use an imager on a CCD, and even spectra, the amount of light as a function of color, that is also a very commonly used object or thing, really, that's used in astronomy for a wide variety of different purposes.
So it sounds like rather than having a common data format, it's more that there are a common set of functionality that the add-on packages leverage, and that's how they are able to interoperate with the other add-ons is through the library functions that are exposed as part of the core, rather than having to adhere to a particular dictionary format, or, for example, for exchanging data between them.
Yeah, exactly. And that's partly because in terms of actual on-disk files, there's been a long history of a shared data format that almost all of astronomy a shared data format that almost all of astronomy has used for the last 20 or 30 years, even back to when most data was stored on magnetic tapes. Astronomers all agreed at that time to share this format that's called FITS. So we didn't have to reinvent the format, we just had to write Python-level tools that would use those sort of on-disk files and let the code interact directly with other code.
Well, that's certainly convenient.
Definitely.
And I noticed that AstroPy adheres to the PSF Code of Conduct, as well as having adopted an enhancement proposal process modeled after PEPs. Can you explain why that's important and what kind of an impact it has had on the community around AstroPy?
I think they're slightly different beasts. So let me start with the PEP-like procedure. So we call them APES, for AstroPy Proposals for Enhancement. So the idea there is that the PEP that has been used by Python is a good way of getting consensus, because you can present a well-formulated idea and then, hopefully a well-formulated idea, and then other people can look at that idea as a whole and then decide whether they think that's worth doing for large changes in Python. And we basically face the exact same need in AstroPy. For example, that SkyCoord class I was talking about that represents a particular point in space, that is required for a wide range of tasks in astronomy. Almost everything you need to know where it was that the telescope was pointed, for example. So that affected a lot of people who might be wanting to use this functionality. So it was good to have a procedure that was sort of outside of the core group of developers, that people could just look and see, here's what the coordinate stuff is going to look like. What do you think about that? And get feedback on it through that mechanism. So we don't use it for smaller changes. So Python definitely, even relatively small changes often go through the PEP sequence. APES we reserve mostly for large things like the layout of an entire major sub-package, or adopting a code of conduct, for example, that are sort of wide-ranging across what at least we think the whole AstroPy community. Whereas smaller changes like adding another function to do some significant task, but just, that's a localized change in the code, we instead use pull requests on GitHub. So that's the APE process. Now, on the question of the code of conduct, we consider this pretty important in part because AstroPy is more than just a code library. It's also intended to be a community of people who agree on how we should go about developing this code library. And inevitably, when you have any at all significantly sized group of people, conflict comes up from time to time, and that conflict can take the form of disagreements about how to do the code, or even harassment at a conference we might be organizing. And we wanted to make sure at the very beginning that we had a clear set of standards that we could all agree on, so that if problems did come up, we could address them immediately. We could say, look, you just sort of did something we kind of thought was sketchy, but rather, look, there is this code of conduct, you agreed to it, and you violated it.
Definitely is important to have a specified body of behavior that you can point to as concrete examples of what is and is not acceptable, because otherwise it's too easy to fall into the, I said this, you said that line of argument, which doesn't get anybody anywhere. So having clearly defined rules up front can greatly reduce and sometimes eliminate that whole line of argument that might come up.
Yeah, absolutely.
And I'm curious if you evaluated a number of other codes of conduct in the space, and if so, what made the PSF code of conduct stand out among them?
We actually started with the PSF code of conduct as in part because we were about to have a conference, a fully organized conference on Python, or on Python in astronomy, and we knew because that would be a larger group, there was a distinct possibility for needing this sort of code of conduct, and it was just a really good starting point. And what we ended up doing was starting from the PSF code of conduct as one that was fairly relevant for us as a group of Python coders, and actually had a whole session at the conference on sort of crowdsourcing, you might say, the code of conduct. And the code of conduct we now use, that's listed on the AstroPy website, came out of this, what we call an unconference session, actually, where a lot of the people involved at the conference helped write it, had a lot of discussion about what we thought were the important elements and which were relevant for us and which weren't, given that we were both astronomy and Python instead of just one or the other.
Yeah, it's definitely valuable to have that kind of feedback and buy-in during the process of creating the code of conduct, because then you don't have a single person or a small group of people saying, this is how the code of conduct has to be, and it's actually buy-in from the whole community, which greatly reduces the amount of pushback that you would get if it needs to be employed, because you can point to it and say, hey, we all agreed on this, everybody worked together, as opposed to somebody arguing, oh, well, I didn't agree to it, it's just something that was imposed upon me. So that definitely seems like it would greatly improve the effectiveness of it.
That's what we hope.
So are there any questions that we didn't ask that you think we should have, or any other topics around AstroPy that you would like to bring up before we move to the picks?
Oh, I would like to mention one piece of functionality that I think is important in AstroPy that I haven't had a chance to talk about too much here, and that's the units package. So what units basically does is provide a way to associate a physical unit like kilometers or minutes or any sort of physical quantity, energy, with a number or a NumPy array. And this has turned out to be an extremely valuable tool for astronomy, certainly, but in fact, as we've talked to other members of other communities that are sort of allied, like physicists who use this, Python, for example, it turns out this is something that a lot of people want. And I think it's worth considering. We haven't made a firm decision on this yet, but it's worth considering whether or not our units package should be separated out of AstroPy to be shared with the wider community, and moreover, whether we should have a larger effort to agree on one units package that does the same sort of stuff that the AstroPy units and quantity packages do.
Yeah, that definitely sounds like it would be immensely valuable for anything that's doing experimentation or analysis on physical quantities. I know that when I was taking physics classes in college, that was, and chemistry classes, that was definitely one of the things that you really had to focus on, is making sure that you're doing the proper conversions between different types of units, and remembering how the different types of units cancel each other out depending on whether it's meters per second squared multiplied by distance, for instance, and how that results in, meters per second. And I can definitely see how that would be valuable outside of just astronomy. And I'm curious if in the library itself, if what you're doing under the covers is actually defining new types that have their own sets of behavior for being able to do those kinds of conversions.
Yeah, they're basically classes that inherit from the NumPy array class, the ND array, I guess it's called. So that's how they work under the hood, but they don't really have to. It's more sort of defining an interface, and there are some people who've, sort of hacked around on it. I don't think any so far public packages, but who've shown that you can basically get away with using some of that machinery to describing this combination of a physical quantity and a number or an array of numbers. And that makes it both an interface, a way to connect different codes written by different people, maybe in very different communities, and a powerful tool for doing exactly what you just said, actually keeping track of your units and not having to worry yourself about exactly what is the conversion from, feet to kilometers or something like that.
Very interesting. So is there anything else that you'd like to bring up?
No, nothing's coming to mind.
Well, with that, we will move into the picks. And for my first pick today, I'm going to choose the Open Culture account on Twitter. It's a Twitter feed that just has a lot of really interesting content. So one of the things that they listed today was it had a brief article and a link to recordings of readings of all of C.S. Lewis's Chronicles of Narnia. There are a few things having to do with Frida Kahlo and some of her work, and it's just a lot of really interesting bits of popular culture from, within the last century or so that you can gain free access to. So a lot of really good content there, definitely worth following. Another project that I've been using for a little while is a Chrome plugin called Citizen X, and what that does is it will actually analyze the sites that you visit, and based on where each of the different companies or sites are located, it will calculate your algorithmic citizenship. So, for instance, if you're viewing a lot of sites that are based out of Germany, then it will calculate your primary algorithmic citizenship as being in Germany or the United States, for instance. And it will actually show you the breakdown of where each of the different sites are located and what your percentage is in terms of your citizenry. So definitely an interesting view of data in terms of how we actually use the web. And my last pick today is a Python library called piprot, which you pass it your requirements.txt files, and it will actually call out to the Python package index and determine how far out of date all of your installed libraries are, and show you what the most up-to-date versions are. So, for instance, if all you're looking to do is run through all of your dependencies and pin new versions, new updated versions in your requirements.txt, then piprot gives you an easy way to do that. And with that, I will pass it to you, Chris.
Okay, since I'm kind of running around like a chicken with my head cut off, today I'm going to keep my picks simple. I'm going to do a podcast trifecta. My first pick is an excellent podcast. It's called The Illusionist. It's part of that Radiotopia group that 99% Invisible that I've gushed on about ad infinitum started. And this is this very, very witty, funny Britisher lady talking about language in really, really amusing ways. It's short, it's edifying, it's interesting, and it's incredibly entertaining. I recommend it. My next pick is a podcast called Criminal, and pardon me, that is a podcast about the law and the people who break it, but from a really interesting perspective. I'll leave it at that, but it's definitely not your average sort of, criminals are bad, okay, perspective. It's definitely very thought-provoking. Again, short and easy listen. And my third pick is a bit more in-depth and a bit more intense. It's called Hardcore History, and it means what it says. The current episode is 3 hours and 20 minutes long, but each episode or series of episodes is just so incredible in terms of its depth. And he has a really great way of relating events in history to the modern era. Like the current episode is about the Spartans versus the Persians, the famous Battle of the 300. And he talks about how Spartans spoke laconically and essentially likened it to, if Clint Eastwood and Batman had a love child, that's the way he would speak, kind of thing. So it's interesting stuff, really, really well written, well produced, very in depth. Can't recommend it hardly enough. And that's it for me. Eric, what kind of picks do you have for us?
Well, I figure I have to start as being an astronomer with pointing everyone to one of what I see as one of the most inspirational sites you can find on the web, which is the Hubble site. So this is hubblesite.org. A great place to go for some of the best and most iconic imagery from the Hubble Space Telescope, which really helps you sort of understand, at least helps me, maybe I should say, understand how vast and beautiful the cosmos is, and helps me understand, even since I can be often deep in the weeds writing code, it helps me understand that the reason why I'm deep in the weeds writing this code is because this is the sort of thing that we can get out of it. So that's .org. Another thing inspired by, in fact, that history podcast that you were just mentioning there, Chris, is something called The Great Courses. So these are a series of audiobooks that are courses on some interesting topic. And I've just recently completed the great course on the history of the ancient world. So I've been a longtime history buff, but I've really found this to be an excellent overview of ancient history, or ancient history is sort of defined as the beginning of urban civilization up until, roughly speaking, the fall of the Roman Empire. Actually, the course has an interesting perspective on where the end of ancient history is, but I won't spoil it for you in case you want to see it yourself.
Excellent. So for anybody who wants to keep in touch with you and follow what you and the AstroPy project are up to, what would be the best way for them to do that?
The best place is always astropy.org, which has a variety of links there for how you contact for specific needs. A more general thing, if you want to just keep up with what the project is doing and what people might be using AstroPy for, is either of the AstroPy mailing lists. So we have one that's just called AstroPy, which is primarily for users, or it's even more wide than just AstroPy, the Python library. It's really for anyone who has just about any sort of question about using Python to do astronomy. And if you're more interested in the details of AstroPy, the library, we have an AstroPy dev mailing list. Again, both of the links for both of these you can find right away just at the AstroPy website, astropy.org.
Great. Well, we really appreciate you taking the time to join us today and talk to us, and particularly taking time out of your preparation to go and do some observations. And I just want to say thank you, and I hope you enjoy your trip and the rest of your evening.
Great, thanks. Thank you for having me. This has been great.